Okay guys, in this next video we're going to talk about another concept in electrochemistry called half reactions. And so the idea here is that a redox reaction can, at least conceptually, if not physically, be divided into two parts, which we call the half reactions. And so the oxidation part of the redox reaction involves a species where the oxidation number increases due to the fact that it loses electrons. Reduction, on the other hand, is where the oxidation number of a species is reduced because it gains electrons. And so we are going to use this redox reaction here as an example to illustrate the half reactions at work. So we see that iron is its oxidation number is increasing. So you go from iron with an oxidation number of 0 in the elemental form to an oxidation state of +2 in the monoatomic ion. Conversely, the copper 2 ion, its oxidation number is reduced from +2 to 0 in the elemental form. And so what we can do is divide the total redox reaction into its two half reactions. And so for the oxidation half reaction, you have iron forming iron 2+ because it loses 2 electrons. For the reduction reaction, you've got copper 2, which gains 2 electrons to give you metallic copper. Okay, so these are the oxidation and reduction components of the total redox reaction that you see here. Now there's a little bit of redox reaction lingo here at the bottom. The term oxidizing agent refers to the species that causes oxidation to occur. And in the process of causing oxidation to occur, the oxidizing agent in turn is reduced. And so the way I like to remember it is I say that the oxidizing agent is reduced. And I always say it to myself in that same way so that I don't forget the rule. Conversely, the reducing agent causes reduction to occur, and in the process, the reducing agent is oxidized. So the oxidizing agent is reduced, the reducing agent is oxidized. Well, let's look at the redox half reactions and try to figure out which of these species is the oxidizing agent and the reducing agent. So you look at the half reactions that you have here, we see that the iron metal is oxidized and the copper 2 ion is reduced. Okay? So the statement, the oxidizing agent is reduced, allows us to identify the copper 2 as the oxidizing agent, and the iron, because it is oxidized, we would identify it as the reducing agent. In this slide, I'm presenting different types of reactions that you'll encounter in chemistry, and I'm showing you both redox versions of those reactions as well as non-redox versions. And so we'll start with the first one here, the combination reaction. So this is a type of reaction in chemistry where multiple things come together to form one thing. And sometimes combination reactions are redox reactions, other times they are not. In this first example, you've got sodium metal combining with chlorine gas to form sodium chloride. Now, one way you can know right away that this is a redox reaction is to recognize that you've got elements on one side and non-elements on the other. By definition, the oxidation numbers of the elements are going to change when you form a compound, right? The oxidation number of sodium is 0. The oxidation number of chlorine atoms in elemental chlorine is 0. But in the compound, they are non-zero. And so you'll recognize immediately that the oxidation numbers have to change. And if the oxidation numbers of the atoms change, then it's a redox reaction because electrons have been transferred. Okay, so that's the secret to recognizing a redox reaction in some cases. If you have elements going to compounds, you know it's a redox reaction. Here is an example of a combination reaction that would be non-redox. And if you carefully work through the oxidation numbers of all of the atoms in this reaction, you'll find that they don't change as you go from reactants to products, and so it's not a redox reaction. A decomposition reaction is the opposite of a combination reaction. Here you've got one compound being decomposed into multiple other species. In this first example here, you've got mercury 2 oxide being decomposed into its elements. And again, you have the elemental form on one side of the reaction where the oxidation numbers are 0, and on the other side you have the elements within a compound where the oxidation numbers are non-zero. Therefore, the oxidation numbers have to change, and so we would be able to immediately recognize this as a redox reaction. Here's an example of a non-redox decomposition reaction. You have calcium carbonate being decomposed into calcium oxide and carbon dioxide gas. If you carefully work through the oxidation numbers of all of the atoms within this reaction, you'll see that they don't change. Therefore, it's not a redox reaction. Displacement reactions are where one element displaces another element in a substance. So here you've got copper metal is displacing silver ion, giving you aqueous copper 2 nitrate and silver metal. Notice that you go from elemental copper on one side to copper ions on the other side, silver ions on one side to elemental silver on the other side. The oxidation numbers have to change, and so you would recognize that as a redox reaction. Here's another example involving zinc and hydrochloric acid. The zinc displaces the hydrogen atoms, giving you aqueous zinc chloride and hydrogen gas. Again, you go from elemental zinc with the 0 oxidation state to zinc ions with the +2 oxidation state. And so since the oxidation numbers change, we know that this is going to be a redox reaction. Combustion reactions, where a substance reacts with elemental oxygen, it burns. These are always redox because the oxidation state of oxygen in the reactants is always 0, but in the products, the oxidation states will typically be -2 for oxygen atoms. And so since the oxidation numbers change as you go from reactants to products, you know that these are redox reactions, and combustion reactions are always redox. Well, the next objective is to be able to balance redox reactions. And so I'm going to be illustrating something called the Halfreaction Method. And for simple redox reactions, the Halfreaction Method is almost not needed. It's almost more work than it's worth. Nevertheless, it's very helpful to illustrate the steps of the Halfreaction Method, which will be necessary when you try to balance redox reactions in acid and base solutions. Okay, so we'll just go through these steps quickly for a simple reaction. The key is you need to balance both atoms and charge in a redox reaction. They both have to be balanced. And so the first step in using the Halfreaction Method is to assign the oxidation numbers to all of the atoms within the skeleton equation. Then you want to split that skeleton equation into its half reactions. So you have to figure out who's being oxidized, who's being reduced. Then you balance the half reactions with respect to atoms and charge, and then you recombine those half reactions in such a way that the electrons in the half reactions will cancel out. So let's illustrate that with an example. So here we've got 2 reactions. I'm going to leave part B as an exercise for you, but we'll do part A explicitly on this slide here. So taking a look at this reaction, you've got zinc is going to zinc 2+, and silver plus is going to silver. Okay. Now at first sight, it may look like it's balanced, right? You've got one zinc here and one there, one silver here and one there. However, this reaction is not balanced with respect to charge, right? You see that there's a +1 charge on the reactant side and a +2 on the product side. So we don't have a balance in the number of electrons for this reaction. Okay, so we want to balance that. Well, you want to assign the oxidation numbers to figure out who's being oxidized and who's being reduced. In this reaction, it's pretty easy. You can tell that the zinc is being oxidized, right? Its oxidation number increases, goes from 0 to +2. The silver ion, however, is being reduced. It goes from +1 to 0. Okay, so we know that zinc is oxidized, silver plus is reduced, and so we can split this reaction into the half reactions. You take the zinc, put it on one side, and the zinc 2+ on the other side. Okay, so that's the first step in balancing the half reactions, is you write down the skeleton half reaction. Then you want to balance that skeleton reaction with respect to atom type first. Okay, in this case, it's already balanced. We've got one zinc on this side and one zinc on the other side. The next step is to balance with respect to charge. And the way that you balance charge is by adding electrons. You can add electrons either to the products or the reactants, but you can only add electrons. You can't do anything else. So in this unbalanced half reaction, we've got a +2 charge over here, but the reactant side is neutral. So how can we balance this reaction by adding electrons? Well, we would add 2 electrons to the product side so that the +2 charge of the zinc is balanced by the minus charges on the 2 electrons. So now this is a balanced half reaction. We want to do the same thing for the reduction reaction. So we take the silver plus, put it on one side, put the reduced form, the silver, on the other side. We balance with respect to atom type. It's already balanced. We've got one silver on each side. Next thing we want to do is balance with respect to charge by adding electrons. Here you wouldn't want to add any electrons to the product side because that wouldn't help you. You need to add electrons to the reactant side. So you add 1 electron to balance that plus charge. Both sides have a neutral charge. So now this is the balanced reduction reaction for silver plus. The final step is to recombine the 2 half reactions in such a way that the electrons will cancel. And notice that this balanced half reaction has 2 electrons on the product side, whereas this one has only 1 electron on the reactant side. And we want to have an equal number of electrons on both the reactants and products when we recombine these 2 half reactions. In order to do that, what we need to do is take this half reaction here and multiply the whole thing by 2, and then add it to that half reaction. And so that's what's illustrated here. And the electrons, since they are the same number of electrons on each side, they cancel out, and you're left with the balanced redox reaction. And if you look carefully here, we have both atom type are balanced, but the charges as well. You have a +2 charge on this side, and you've got a +2 charge on the product side. So that's the half reaction method for a simple redox reaction. Like I said, I'll leave part B as an exercise for you guys to think about. What we're going to turn to next is the more complicated task of balancing redox reactions in acidic solution, followed by balancing redox reactions in basic solution. And there's more steps. And what you're going to find, it would be very difficult to balance these reactions without following this algorithm. You know, for this reaction here, you probably could have balanced that by inspection, right? Just put a 2 in front of the silvers, and then it would be balanced. Likewise, for this one, all you need to do is put a 3 in front of the magnesium. You don't really need the half reaction method for that. However, for balancing in acidic solutions and basic solutions, you're going to find that the result you would not have predicted just by inspecting the skeleton equation. So the first couple steps are the same. You want to assign oxidation numbers to your skeleton redox reaction so that you can split it into 2 half reactions. Here's where the difference comes in for acidic solutions. What you want to do is balance the half reactions with respect to each atom type except oxygen and hydrogen. You're going to save those for the next steps. So once you've got every other atom balanced, you then balance oxygen, and you do it in a funny way. You do it by adding water molecules. Now that you've introduced water molecules, you've added a bunch of protons to the reaction. You balance those by adding acid. You add H+. So once you've got all of the atoms balanced, then you move on to balancing the charge by adding electrons. And then you recombine the half reactions in such a way that the electrons will cancel. You're probably going to have to do a bit of cancellation in that final redox reaction, combining terms and canceling species that appear on both sides. And so we'll see some examples of that. I think first I wanted to give you the steps for balancing in basic solutions. They are the same as the steps for the acidic solutions. So when you're dealing with a redox reaction in basic conditions, you do all 4 of the acid steps, but then there's a couple more. Okay, so when you've got a basic solution, you balance it as if it were in an acid solution, and then you convert it into a basic reaction by adding hydroxide to both sides of the reaction. So for every H+ that remains in your redox reaction, you will add a hydroxide to each side. And then sides that contain both H+ and hydroxide, you combine those to make water, and you may need to cancel out some waters in your final redox reaction. So we're going to do some examples of both acidic and basic redox balancing. Okay, so here's our skeleton reaction that we're being asked to balance. What you want to do is assign oxidation numbers to each atom in the species, and that's what I've done here. So, you would assign an oxidation number of -2 to the oxygen. There's 4 of them. That plus the manganese oxidation number needs to add up to -1. And so you can use the tricks that we learned in the last video to figure out that the manganese is in a +7 oxidation state. The chromium 3 ion here, let's see, it's a monoatomic ion, so its oxidation state is +3. The manganese here is a monoatomic ion with a +2 charge, so it's a +2 oxidation state. And then for this dichromate ion, you need to figure out what would be the oxidation number of the chromium and the oxygen. You start with oxygen, you assign it a -2, and then you use the fact that the whole sum of all of the oxidation numbers must add up to -2, and so you can use that to deduce the oxidation number of the chromium. So there's a bit of work that goes into figuring out these oxidation states. Once you have them, then it makes it easy to identify which species is being oxidized and which species is being reduced. We'll take a look at the permanganate ion here. We see that the manganese ion, or the manganese, is in a +7 oxidation state on the reactants, but then that drops down to a +2 oxidation state in the products. So the permanganate is reduced. The chromium ion, on the other hand, starts out at a +3 and then is oxidized to a +6 oxidation state. Okay, so the chromium 3 undergoes oxidation. So we're going to start with oxidation, like I like to do. And so we've got the chromium 3 on the left. We've got the dichromate ion on the right. Okay, the first step in balancing the half reaction is to balance with respect to atom type, except oxygen and hydrogen. That's the rule for acidic conditions. So we see that the chromiums are unbalanced. So I'm going to put a 2 in front of the chromium 3 ion on the left so that I've got 2 chromiums on each side. Once we've got the non-oxygen and non-hydrogen atoms balanced, we then turn to balancing oxygen. And you do that by adding water molecules. So in this second step here, we've got 7 oxygens on the right and none on the left. To balance the oxygens, we add 7 water molecules to the left. Okay, so now the oxygens are also balanced. However, this introduced hydrogen on the left, and we don't have any on the right, so we need to add in hydrogens. We do that by adding acid. That's what makes this acidic conditions. So we've got a total of 14 hydrogens over here, so we're going to add 14 H+ to this side. So now all of the atom types are balanced. The last step in balancing the half reaction involves balancing the charge, and you do that by adding electrons. So you've got a total of +6 on the reactant side, and then you've got 14 minus 2, you've got a total of plus 12 on this side, so 6 and 12 on this side. All you can do is add electrons, so we're going to add 6 electrons to the right-hand side. That's going to bring the right-hand side down to plus 6. The left-hand side is plus 6. So this is the balanced half reaction under acidic conditions. Now what we want to do is repeat the procedure for the reduction step. Okay, and so we said earlier that the permanganate was reduced to manganese 2. So we start with the skeleton reduction reaction. The number of manganese atoms is already balanced, so we'll turn to oxygen next, and we do that by adding water molecules. So there's 4 oxygens on the left, so we add 4 water molecules on the right. This introduces 8 hydrogens on the right, so we need to add 8 H pluses to the left. Now all of the atom types are balanced, but we want to balance the charge next. You do that by adding electrons. We see that we've got a plus 2 charge on the right, and we've got this would be a plus 7 charge on the left. So what we need to do is add 5 electrons to the left to bring the total charge down to plus 2 on the left. And so that's what we have here. So this is the balanced reduction reaction under acidic conditions. The last step is to combine this reduction reaction, which involves 5 electrons, with this oxidation reaction that involves 6 electrons, in such a way that the electrons cancel out. The way you do that is by multiplying this equation by 5, so that you'll have a total of 30 electrons on the product side. You multiply this reaction by 6, and that's going to give you 30 electrons on the reactant side, and then you add them together. Okay, so that's what's been done here in this step. So I multiplied this by 6 and added it to this reaction multiplied by 5. Okay, and it gave me this reaction with these stoichiometric coefficients. And then what I want to do is I want to cancel out species that, well, actually these two intermediate steps here. This is me multiplying, let's see, this reaction by 5. Okay, so this reaction multiplied by 5 gives us this first reaction here. And then this second reaction is this reaction multiplied by 6. Then what I do is I combine them. I add them together. And what we see here, I believe, is the balanced reaction after I have canceled out waters that appear on both sides and H pluses that appear on both sides. Right? You see that you're going to have 35 waters on this side, 24 waters on that side. The difference is 11 waters. You're going to have 48 H pluses on the left and 70 on the right. The difference is 22 H pluses. And if you look carefully at this balanced reaction, you'll find that it is balanced with respect to all atom types and charge. And you can always recheck at the end to make sure that you've got the balanced reaction. Let's see, I believe it's the same reaction, but now we're being asked to balance it as a reaction in basic solution. Okay, so in order to balance this reaction under basic conditions, you have to do all of this work that we've done and arrive at this equation. And then what we do is we convert it into a basic solution. You do that by looking at how many H pluses you have in the reaction. Here we've got 22 H pluses on the product side. And what you do then would be to add 22 hydroxides to both sides of the reaction. So I'll add 22 hydroxides on the left and 22 hydroxides on the right. And then you combine, in this case on the right, you combine all of these H pluses and hydroxides to make 22 waters. Okay, and that converts it into a basic solution. And then at that point, you're probably going to need to cancel some things out. So we see that we've got 11 waters here and 22 waters there. So I need to cancel that out to give me the difference of 11 waters on the right-hand side. Once we've done that, we're left with the balanced redox reaction for basic conditions. Okay, so it's quite an algorithm to get through this, but as you can see, I mean, there's no way you would have predicted from this that that would be the result without going through all of these different steps. And so this is something you need to practice. On your assessment, you can expect 3 balancing problems. 1, a simple redox reaction that needs to be balanced. 2, a reaction that needs to be balanced under acidic conditions. And 3, a reaction that needs to be balanced under basic conditions. Okay, so you want to get some practice in doing this algorithm. So I'm going to go ahead and stop the video right there.